All right, so in class we had a request, or at the end of class on Wednesday, today, we had a request for a problem work through for one of the dimensional analysis problems from the Chapter 1 worksheet. And the dimensional analysis problems are problems 9 through, I think, 14. And this technique is something that right now may seem kind of silly with the types of problems that we're doing here. But this is a technique that is crucial later on in the semester when we get into stoichiometry. So we start off introducing this technique so that you guys can start getting used to it. And while some of these problems have many other ways that you can go about solving for the correct answer, the goal here is to solve it with dimensional analysis and with only the conversion factors that I'm giving you at the top of the problem. And I should say any conversion factors that you should technically know off the top of your head. And I'll try to point that out as there's, I think, one of them. Yeah, I think there's only one of them in this example that I'm going to do. So anyways, I want to really point out that for the first midterm, this concept will definitely be tested on, and that it will be part of a free response problem that has partial credit. And the partial credit will involve doing it in the way that I'm expecting you to, which is with dimensional analysis. So if you are not setting things up correctly, if you're not showing these steps, for how we do dimensional analysis, you're not going to get full credit on a problem like that. So yes, you can get the correct answer with other methods, but if the whole goal here is for you guys to learn dimensional analysis, then that is why that problem is going to be on the test. It is to test whether or not you understand the method of dimensional analysis. So keep that in mind as we're, doing these problems. I know it's very tempting to just solve them in a way that you are comfortable with, but the goal here is to push you outside your comfort zone if you're not comfortable with dimensional analysis, and get you guys more comfortable with it so that this is not something that hinders your ability to learn about the higher level concepts when we get to stoichiometry. And we'll see this in other situations before we get to stoichiometry as well. So I will pretty much always fall back on showing dimensional analysis, and you should too. Okay. With this problem, one of the hardest things about these sort of word problems is usually trying to figure out where to start and what in the problem is actually being given to you as a conversion factor. And I apologize if you're watching the little tiny video of me up in the corner. I am going to be looking down quite a bit as I write this out on my tablet for recording this. So, I decided to include my image just so that there was some sort of face that you could look at if you wanted to. But I am going to be looking down for most of this problem. So just keep that in mind. Okay, so for this problem, we are starting with a fishing boat that has spilled 9 barrels of oil into the ocean, and that is actually going to be our starting point, the 9.0 barrels. And everything else that's given to us in the problem is either part of what we're being asked to do or is information that we can use to get to the final answer. Only one of these other pieces of information is what I would refer to as a conversion factor, and that is the fact that it says each barrel contains 42 gallons. Let's recognize that if you're going to write this as an equivalence statement, that would mean that 1 barrel equals 42 gallons. And remember, any equivalence statement, like the ones that I've given you under these useful conversion factors at the top, any equivalence statement can be used as a conversion factor by taking one side of the equivalence statement and using it in the numerator or the denominator of a ratio or a fraction, and then using the other side of the equivalence statement in the opposite position. And it really doesn't matter which spot you put it in, whether in this case, whether the 1 barrel ends up in the numerator or ends up in the denominator. It doesn't matter in terms of what's correct, I would say, about writing a conversion factor. You can use it either way, but the problem itself usually dictates how that setup should appear. So it is important to think about which one needs to be in the numerator and which one needs to be in the denominator based on where we need to go with the units, like what unit are we starting with and what unit are we trying to end up with. Now, because I know I'm starting with the 9 barrels, one of the other things that I like to do with problems like this is actually think through the conversions that I'm going to do first before I start to write them all out. And I call this coming up with a roadmap for the problem. So for this problem, we are starting with barrels and we're going to convert to something else, right? And so if we note here, the conversion factor that was given to us, the fact that each barrel contains 42 gallons, that is something that will allow us to convert barrels into gallons. And so it would be feasible to say here that if we're starting with barrels, probably the next thing we want to do is get this value into gallons, right? Getting it into gallons is going to give us a volume that is being spilled. And if we notice here, the question is, if the oil film on the ocean is a certain thickness, how many square meters will the oil slick cover? So what that means is if we have a height for the thickness of the film, then we can get the area of the film just by keeping in mind how volume is defined. And so that will be kind of an extra step in this problem that's not strictly part of the dimensional analysis, but is crucial for solving the problem. But what is important about that is we notice that our final answer needs to be in square meters, but that in order to get there, we're going to have to use a thickness that's in nanometers. Now, there's different options you could choose for what unit you want to end up in with this whole process. And you know, there's not a right or a wrong way to necessarily do this in terms of which units you convert to first. So I'm going to do it one way, but if you manage to do it a slightly different way, as long as you're getting the correct answer and you understand how you got there, then that's probably fine, right? So it's okay if you did this a little bit differently than I'm going to do it. For my purpose, since I know that I have a volume in gallons and that I'm eventually going to want to use that volume and this height, this thickness to get an area, I'm going to go with converting into the units that this height is given in, so that when I get to that step, I've already got the units that I need to take the volume and the height and get an area. Obviously, that's going to give me an area that has units of nanometers squared. So at the end, I'm also going to have to do one final conversion to get into square meters. So that's the approach I'm going to be using. But to go back to our roadmap here, our volume right now is in gallons. It's not in nanometers cubed. So we need to get from gallons to nanometers cubed. And so first, we need to recognize, well, how do we get from the metric system of volume into from the English system of volume, which is the gallons that we have here, into the metric system of volume, if the goal is going to be to get into nanometers cubed. And so if we notice up top here, this unit conversion that we have for gallons to liters, that's going to get us from the English system into the metric system. So after I go from barrels to gallons, I can use that conversion factor to go from gallons to liters. Now, liters is a volume unit that is a standard unit, but we can also express volume as a derived unit in terms of length cubed, right? And that's where we're headed with this problem. If we're trying to get to nanometers cubed for our volume, then we need to go from the standard unit of volume, which is liters, into a derived unit in terms of length. And the connection between that is the fact that we know that 1 milliliter is equal to 1 centimeter cubed, or 1 cubic centimeter. And that is one of these conversion factors that I did not include at the top because you should know this one. This one you should have memorized. You're going to use it so many times throughout various science courses that it's just to your benefit to make sure you have that memorized. So since this conversion goes from milliliters to cubic centimeters, that means I need to get liters into milliliters first, and then I can take the milliliters into cubic centimeters. Now, once I'm into cubic centimeters, I'm just 2 steps away from getting to cubic nanometers because I could go to cubic meters first, and then I could go to cubic nanometers. And so this path that I've outlined up top here is going to be our roadmap for this process. And each arrow in here basically represents a conversion factor that's going to be needed to go from one unit to the next. So if I've got my 9 barrels, I'm going to go 42 gallons for every 1 barrel for my first conversion factor. And notice that I'm setting it up so that barrels is going to cancel out. So barrels is on the bottom in the conversion factor in order to cancel out with the barrels in the original number, which we expect to be on the top. From gallons to liters, I'm going to use the conversion factor up top, and I want to end up in liters. So that means the liters value goes on top and the gallons value goes on the bottom. from liters to milliliters, I'm going to use that conversion factor we just mentioned. Or sorry, I got to get to milliliters first. Whoops. And then we can use that conversion factor. So for this, you can do, if you know that there's 1,000 milliliters in 1 liter, a lot of people have that memorized. That's a totally fine way to write this. Okay, now we can get into the cubic centimeters unit by doing 1 cubic centimeter over 1 milliliter. Again, using this conversion factor up top here that you should know off the top of your head. And then we've got these last 2 steps. Now, one of the things that has happened at this point is we have now changed to a unit that has a cubed value on it. So the conversion factor I'm going to use next relates centimeters to meters. We know that there's 100 centimeters in a meter, but that is not centimeters cubed. So in order to take care of the cube, I need to cube this entire conversion factor. So I have 1 meter over 100 centimeters, and that whole thing is going to be cubed. Same thing for going from meters into nanometers. I know that 1 nanometer is equal to 1 times 10 to the 9th meters, and I'm going to cube that whole thing. Now, when I go to type this into my calculator, I'm going to talk through this. I'm going to do 9 barrels times 42 times 3.78541 times 1,000. Notice I'm skipping all of the ones so far. So this last step here, I don't really need to do anything. It's just multiplying by 1. But then I get to this thing where I have it cubed. So if I've done 9 times 42 times 3.78541 times 1,000, now I'm going to divide by 100 cubed, right? So I have to cube that value when I go to type this in. Same thing with the last step here. I'm going to take 1 times 10 to the negative 9th. I'm going to be dividing by that value, and I'm going to be cubing it, right? So it's 1 times 10 to the negative 9th cubed that I'm dividing by. Now, if you're a little shaky on order of operations in your calculator, you may have a time typing this out in the calculator correctly. So definitely practice that a bit if you're not getting the right answer. Now, 1.43 times 10 to the 27th nanometers cubed is the answer I'm going to get here. And so now I'm going to use the relationship between volume and height. So volume times length times width times height, or sorry, volume equals length times width times height. And the length and the width here represent the area. So volume therefore equals, volume equals the area, which is what we're interested in, times the height. And so if I want to solve for area here, I can rearrange this and recognize that the area is going to be equal to the volume divided by the height. So to get my area here, I'm going to start with my 1.43 times 10 to the 27th nanometers cubed, and I'm going to divide that by the height I was given, which if I come back up here was the 2.5 times 10 to the 2 nanometers thick. And that's going to give me an area of 5.72 times 10 to the 24th nanometers squared. So now I've got my area in nanometers squared. I just need to convert it into meters, or yeah, because I want my final answer in meters squared. So the 5.72 to the 24th nanometers, oops, not cubed, squared. I'm then going to multiply that by the conversion factor between meters and nanometers, but also squared, right? Again, noting that the unit here, because it has a square, means I need to square my conversion factor. So this would be 5.72 times 10 to the 24th times 1 times 10 to the negative 9th squared, right? So you want to square that value when you multiply these together. And that's going to give 5.72 times 10 to the 6th meters squared as my final answer. Now, in the last minute that I have left here before I'm going to max out my recording at 15 minutes, let me just talk sig figs real quick. So sig figs 9.0, that has 2 sig figs. And when we're looking at these conversion factors, for the most part, none of them are going to limit those sig figs because most of these are within the same unit system. And so they have basically infinite sig figs. So pretty much all of these factors right here, those are all infinite sig figs. And then these values that I gave you guys at the beginning all have at least 2 sig figs. 1 barrel is a counted value. That's an exact number. So that also has infinite sig figs. So if we have 2 sig figs from the 9.0, then I have 2 sig figs in this intermediate answer that I calculated, the 1.43. that carries down here. It carries to my second intermediate answer, and it carries over to my final answer. So 5.7 times 10 to the 6 meters squared.